Dynamics in one dimension, that's what we're starting off today. So we just finished Unit A. You just wrote your exam. Everyone was here wrote it, right? Okay. So now this would be like Unit B. Okay, so expect an exam, roughly a month from now. Just like kinematics was about a month, dynamics will be about a month. Expect a couple labs. We're only going to do a couple demos today. We have to go through Newton's laws of motion before we can really start to really get into anything. So there's 3 laws that we have to go through. Your understanding of those 3 laws are paramount to your success. Don't just like read them once or twice and then just assume that you're going to understand it. You could read it 17 times and you still not might understand it. Okay, so that's why we have to go through examples, and we're going to have to sort of hash out some misconceptions, and eventually, hopefully, you guys will end up with some mastery understanding. Okay, so let's just start off with Newton's first law. So again, there will be a certain amount of notes before we can even get started. So Newton's first law, called the law of inertia. Hey, got a light slip? Go get one. You can drop your books off if you want. Or not, whatever. Okay. So, the law of inertia. And you will have to reproduce these definitions on the daily quizzes. They don't have to be like word for word, but you should have a pretty good understanding of it when you write it down. Okay, so Newton's first law, the law of inertia. And this is the famous law. You guys have probably heard it in everyday language. So I'll just get it out there, and then we'll talk about it. Okay, so here's Newton's first law. And have you guys ever heard of this before in your life? You've seen this before? Yeah, so an object is either going to stay at rest or it's going to stay in motion unless it's acted upon by an unbalanced force. Okay, so we're going to do a couple demos with this. We can do one right now using this pen. Okay, so right now, if you think about this pen, is the pen in motion or is it at rest? So this object is at rest. It's not moving, aside from my hand shaking. Okay, so we say that the forces that are acting on this pen are balanced. So right now, what forces are acting on this pen? Does anybody know? There's a gravitational force that always happens to objects on Earth, which always pulls down because it goes towards the center of the Earth. Now, what's opposing that? What's stopping it? Yeah, the book. The book pushes in the opposite direction and balances it, and it's called the normal force. That's good. And the normal force is, in math and science, normal is used for perpendicular. So the force is perpendicular to the surface. So what happens when I remove the book? It just falls. So what happened? the object was at rest until acted upon by an, what's key there? It's highlighted. Unbalanced force. Okay? So that was an example where the object was at rest. So let's head over into the physics lab and I will demonstrate an object in motion. Okay, so the demo's over. Let's keep going. Let's draw a little flow chart. Okay, so we're going to draw a flow chart. Forces balanced. So if the forces are balanced, the object could be at rest, or the object could be in motion. Good. So if the object's at rest, its velocity is 0, and if the object's in motion, its velocity is not 0. Come on in. You got a lead slip? Go get a lead slip. Yeah, so the acceleration will be 0, and here the acceleration is also 0. And an object at rest will stay at rest, and an object in motion will stay in motion. And of course, staying in motion in the same speed and direction. So have you guys ever driven in a car? How many of you guys drink coffee? Ever? You ever drive in a car with a coffee with no lid on it and watch it? It's tough, right? You watch like the surface of the liquid will be moving as the car like changes direction, or if it suddenly stops, or if it suddenly speeds up. Okay? Yeah, good. Right? So imagine the coffee cup. Okay, let's do an example. All right. Okay, so example, coffee cup. In a car with no lid. Okay, so if you start accelerating, where does that coffee end up? On your lap or in the dash? Like by the windshield. On your lap or on the dash? Good, good. Spills on the lap. Because it wants to stay where it's at, but yet you're moving forward. Or backward, however, which way you're going. Let's just imagine we're accelerating forward, like everyday driving. Okay. So what happens when you make turns? And does it spill? So if I turn to the left, it spills on the right. So why is that? It wants to stay where it's at. You go to the left, it's still there. It's left over on the right. Spill on the opposite side. And then if you stop suddenly, it spills on you or on the dash? On the dash, good. So Newton's first law keeps doing what it's doing. You know, if you're just talking to some everyday language, you're like, explain Newton's law to me. Newton's first law. Well, it just keeps doing what it's doing, you know. It doesn't go anywhere. It just stays where it was, right? And you interpret it that it's going to the left, right? Yeah. Okay. So what we're talking about is this tendency to resist change. I'm driving in my car, I got my coffee in my hand, I'm all happy. Maybe it's Saturday morning, maybe I'm gonna go off to my kids' hockey or something. Got my coffee, no lid. We're driving. Suddenly I stop. Where does that coffee go? Say my girlfriend's driving, I'm holding the coffee cup. So we're driving, say we're driving 60 kilometers an hour, we hit the brakes. Where's that coffee go? Windshield, and I'm pissed off, right? Right? So what happened? The coffee wants to keep doing what it's doing. And this is the tendency to resist change, and they have a special word for this. It's the law of inertia. So think about inertia as like, I heard this phrase when I was at a job before, you know, is it hard to change a big thing? Like, say all the kids in East Glen are doing something and we want to change that. Would it be hard to everybody to change that? Yeah. But if it's just like one person, is it easier to just for one person to change? Is it easier for like a small powerboat to turn left, or is it easier for like a big, cruiser to turn left? Which one's easier? Right? So this is what I mean by inertia. Like, and it all depends on something. What does inertia depend on? It depends solely on, who said that? Good. Say it louder. Yeah, mass. Depends solely on mass. Okay? A lot of you guys are football players, right? Some of you got even basketball players. So like when you go to juke somebody, you know juke? What's a juke? Like when you like a quick move in hockey, they call it quick dangle or something. Like it's like a little fake like this. If you're a big dude, like a lineman, is it easy to do those jukes? If you're the quicker, smaller, agile running back, is it easier to make those jukes? Yeah, so it depends on your mass. If you're a big, heavy guy, it's hard for you to, if you want to deke out a bear, maybe not a bear, those guys are savage. You want to deke out like an elk or something, it's big mass. You're going to do some zigzags. Don't run straight. Oh, you guys are so particular. I'm just trying to get some examples for you. Okay. So this tendency to resist change, or we could say it a little bit differently. We could say it's like the tendency of an object to resist acceleration. And what we'll come to learn is that forces cause acceleration. Tendency of an object to resist acceleration. It's like for inertia, you could think of it like this or like this. Because this, like, to resist change is sort of vague. Like, what do you mean change? Like, change in speed, change in distance, change in displacement? Like, what are you referring to? So we're talking about changes in speed. Is it, for a big guy, like say a 300-pound guy, is it easy for him to change speeds compared to like Connor McDavid? You ever watch Connor McDavid? That guy takes off in different directions so fast, and he's really lean and skinny and muscular. You think like a 300-pound dude on skates could do that stuff? No, because a 300-pound dude has all this mass, and it's really difficult to change his speeds, whereas a smaller, leaner guy has a better chance at that. You guys kind of clear on that? Okay. So there's Newton's first law. Now we're going to start talking about these balanced forces. Okay, so we're going to title the next thing Balanced Forces. And this is going to play a major role in your problem solving, these balanced forces. So often we're going to be drawing these things called free body diagrams, and we have to identify the forces that are balanced and the forces that are unbalanced. Because as soon as we find an unbalanced force, we're going to be able to locate an acceleration, and then once we have the acceleration, we can usually solve the problem. Okay, so all you need to do is draw like a table or a floor or something like this. Draw a table, okay, and then draw a book on it. And this book is labeled physics. Come on in. I'll turn it off, yeah. Oh, go on in, Alan, go on in. Okay, guys, bring it back. Okay, so just imagine my physics book just sitting on the table, just like that. Okay, that's all that's happening. Okay, Alan, you'll just have to get the notes from the previous couple pages. Only 2 pages. So there's your physics book. Is the physics book in motion, or is it at rest? Okay, so if it's at rest, the forces must be... Say it again. If the object is not accelerating, the forces must be balanced. Okay, so which forces are acting on this book? There's a downward force. That's the acceleration, yeah. So the force is the weight. We'll get to that. So there's a downward force, and what opposes that is an upward force coming from the surface, or in this case, the table. Okay? So gravity pulls downward on the book. And the table pushes upward on the book. Yeah, but the ground is holding the table up.
Well, yeah, but like let's say we threw it into space, it would have a little bit of gravity to it since it's in some mass.
Yeah, like we're just focusing on a little thing at a time here. That's all we're doing. Okay, so how does the table know to, push back the exact amount of the book? Well, it doesn't. So like, if I push down on the book, is it accelerating? Is the book moving? But the upward force has to match my downward force. What if I put an elephant on this table? Table might break, right? And then the elephant would accelerate down. So not all normal forces can handle all the weight of the object, okay? So right now the normal force is balanced with the gravitational force. If I have to push on this, not accelerating, so now the normal force has matched the weight of the book and the extra applied force I've given it. So the normal force just responds to the gravitational force or the downward force, okay? I don't think the principal would like that one. He calls those OH&S issues. Okay, so the two forces are equal in magnitude and opposite in direction. And they call this, in physics, they call this equilibrium. And we talked about the fact that there is no unbalanced force. And if there's no unbalanced force, so it maintains its state of motion. What is the state of motion of this object, prior to the forces? Is it in motion? Like, is it moving, or is it stationary? It's stationary. So if all the forces acting on it are balanced, it's going to stay stationary. If that physics book was floating through space at some speed, and two people on opposite ends started pushing on it somehow, that thing would still stay moving. Okay? Does that make sense? That's something we're going to hash out later. Like, objects can stay moving even though there's no forces being applied. And it feels weird. Like, how do I move this stapler? I got to apply a force. Well, if I remove the force, it stops moving. Well, you need a force to move something. Turns out it's not the case. Okay, let's go to another page here. We can start talking about some unbalanced force. We'll get to that, yeah.
Can Anthony Russo please come to the office? Anthony Russo, come to the office.
Okay, so draw the physics book again. The physics book has the same upward force and the same downward force that are balanced, but this time the book is in motion to the right. Okay, so now the book is in motion left to right. So left to right. Watch the book. What happened to the book? It stopped. It had motion. It had motion, but then the motion ceased. So did it maintain its state of motion, or did the motion change? So if it's slowing down from my initial speed to a stop, it must be accelerating. If it's accelerating, it must have some unbalanced force. So where's the unbalanced force? The motion is left to right. So what's stopping it? Everybody knows this. Friction. Which way do I point the arrow for friction? Good, the opposite. So here's your force of friction. Okay, the book is in motion, sliding from left to right. Okay, sometime in the prior history of the book, it may have been given a push. We don't know. But you watched me, I gave it a push. Our focus, however, is on the current situation. And no one is pushing it. And then in brackets, a force is not needed to keep an object in motion. Okay, so this is important to note, this thing in the brackets at the end. A force is not needed to keep an object in motion. Okay, so some prior history of the book, some force is applied. The book continues to move, even though the force is no longer being applied to it. Then the book slows down. So it's accelerating. If the book is slowing down, it's accelerating. That acceleration and the force vector that goes with it has to be drawn in the same direction. That force vector, force of friction, pointing to your left, is it balanced or unbalanced? We've talked about this a few times. This is unbalanced. You don't see anything on the right-hand side, right? The up and down are balanced, but the left and right are not balanced. So if there's an unbalanced force, there's going to be some acceleration. And in this case, the acceleration is negative because the book is slowing down due to friction. So let's formalize that. The friction between the table and the book's surfaces exerts a leftward force upon the rightward moving book. The vertical forces are balanced. But the unbalanced force of friction acts to slow the book. The book is not in equilibrium. And therefore accelerates. Okay, I'll give you a second to jot this down, and then I'll show you a nice little demonstration called the rocket sled. Okay, so just let me know when you have the notes down. You guys good? Couple people at the back. All right, good? Who keeps saying that? Oh, you're okay. Good? Okay. What were you doing this whole other time? Listening? Learning? Okay, we good?
Oh my. No, wait.
Chris, do you have it all down? Okay, give it to him. Okay, you guys ready for this? This is a rocket sledder. Okay? Let's give the rocket sledder an applied force. Actually, let's stop. I want to stop. I gotta reset this. Let me just reset it. We can talk about it. Okay. So right now, if you look at the free body diagram, we're going to talk about those a little bit later. You can see that we have the weight of the sled, obviously downward, and then this normal force from the ground pushing upward. Okay, so watch what happens to the arrows as I add more weight, or in this case, more mass, pardon me, if I add more mass. So what's happening to the sizes of the arrows? They're getting bigger, and are they matched? So they're balanced. Is this guy accelerating anywhere? No. Okay, let's give him a little bit of applied force to the right. Let's give him a 50 Newton force to the right. What's happening? What's changing? So if you were to graph this, what would it look like on the whiteboard here? Like this, right? Right now, this seems like it'll never end, so we have this arrow on here, okay? We know that though, that couldn't happen forever, so it'll stop somewhere. Okay, so do you see any oppositional force to this applied force? Anything opposing it in the left? No. So he's going to constantly accelerate. Is his speed continually changing? Right. So let's put on some friction. Well, he's going too fast, maybe. He's probably going to hit some terminal velocity. Better give him some friction. What's happening now? I got the friction on there. What's up with the friction? Is it greater force or a bigger or a smaller force? It's greater. So what's happening? He's slowing down. Okay, let's take off some weight. What's going to happen to that frictional force? Take off some weight. What's going to happen at 50? Right now, the leftward force is slightly larger. So what's happening? Accelerating negatively, right? Slowing down. What happens when they match? What stops? The acceleration stops. But what does Newton's first law say? An object in motion wants to stay in motion. What's happening with his speed? Same. Are all the forces balanced? So if there's no unbalanced force, it's going to keep doing what it's doing. Remember that? Keeps doing what it's doing. I'll accept that. Okay. So a couple things went on when we added weight, or pardon me, when we added mass, the frictional force went up. We'll talk about that soon. These free body diagrams, we'll talk about that. That's crucial to this part of this unit. Okay, and we'll talk about the Newton, we'll talk about net force, what does that mean, and velocity changing and acceleration, that's stuff from kinematics in Unit 1, so you should already be aware of stuff like that. Okay, so that's the rocket sledder. Isn't that sweet? Rocket sledder. Okay. Yeah, you could do that. Okay, so let's go back to the notes. So there's no homework tonight. However, maybe I'll give you some homework. We'll see. Yeah, what's today, Wednesday? Yeah, we got homework. Lots of homework. Only because you guys complained. Okay, so let's do some, we gotta do some more notes. Okay, so let's talk some more about force. Okay, so what is force? A force is going to be a push or a pull. Okay, so a force is a push or a pull on an object resulting from the object's interaction with another object. So what does this tell you about forces? You'll need more than one thing, right? So an object has to interact with another object. And once that interaction is gone, then the force is subsequently gone as well. Okay, so just jot that down. If the interaction ceases, you know that word? Cease? Stops. If the interaction ceases, the two objects no longer experience the force. Okay, so forces only exist as a result of an interaction. Okay, so what type of forces are there? Little flow chart. Okay, so we're gonna keep this quite simple. It's only physics 20. You know, we're not in like master's degree physics studies right now. We're just in the beginning, so we're gonna keep it simple, right? Okay. So we're gonna talk about contact forces. If I could spell. Contact forces, and then this other one that you guys are familiar with, but may not know what it's called. They call it action at a distance. So obviously, in order to change the acceleration of an object, you got to touch it, right? If I want to make this calculator speed up, I got to throw it, right? Good catch. Right? So if I want Batman to go flying, I'm going to pick him up, I'm going to apply a force, and I'm going to throw him. I have to touch him, right? I got to pick up Batman and I got to throw him. But what about this other thing, action at a distance? Have you guys ever experienced forces where you didn't actually have to touch? Give me some examples. No wind touches you, the particles of the air hit you. Go for it, Phelan. Gravity, lovely. How does the moon know to orbit the Earth? How? Okay, so there's some force occurring. Go for it. Magnetism, excellent. And there's one more for this simple list. One more. Go for it. Close. Heat. We're talking about force, not energy. Electricity, very good. I didn't hear you. I didn't hear you. So you walk across the room, you're at home, you're walking across the room in your socks, and you're walking on the rug. What's happening? You're stealing electrons. You're stealing electrons from the rug, and it's going through your body, and then you go and touch the door. You feel a force. You don't even touch the door. It's like, gotcha. Okay, so action at a distance. The big one in Physics 20 for you guys is gravity. We're going to talk about gravity in Physics 20. Magnetism, electricity is left for Physics 30. Okay, so let's go into the contact forces that you're going to be working with.
Jordan Lindstrom, please come to the office. Jordan Lindstrom, come to the office.
Okay, so we've all already mentioned the force of friction. What do you call the force when you hang a mast by a rope? What do you call that? Starts with the T. Louder. Very good. Is that you, Kane? Tension. Okay, we've already talked about the force that is perpendicular to the surface. It keeps that stapler not from accelerating towards the center of the earth. What's keeping that stapler up? The normal force. Okay, in physics and math, normal means perpendicular. So I'm just going to give you that right here. Normal means perpendicular. Perpendicular at a 90 degree. Air resistance, you might see once in a while in Physics 20, but very rare, because it's very hard to predict and not easily quantified, so they keep it out of physics in high school curriculum, air resistance. Yeah. The temperatures, all that stuff. Yeah. Okay. So, and then we have the applied force, and this could be anything from, you slapping your friend in the face to, throwing a ball, pushing a crate, picking up a weight. So these are just like anything that you do. And then the last one for this list, this simple list, will be the spring force. And we're going to be working with springs in the physics lab. Okay. We're actually going to do a friction lab, and you'll get to work with newtons and springs and forces. So you will get to do a real lab, not a Goduncan lab. All right, so let's keep going. All right, so we talk about the Newton. What the heck is a Newton? 1 Newton is the unit for force. Good. And of course, it's named after Isaac Newton, one of the most important human beings ever to have lived. And do you guys know the formula from Newton's second law? Force equals mass times acceleration. So a lot of people already know this. What's the unit for mass in standard metric? kg. And then acceleration is meter per second per second. So meter per second square. So that's your unit for force. Okay, this is the amount of force required to give 1 kilogram an acceleration of 1 meter per second per second. Meter per second square, same thing. Okay. Something a lot of you still need to work on after watching or marking your tests. Force is a vector quantity. You will never get away from this in physics. So if you didn't quite master it in the first unit, you still have to work on it. Okay, and we will be doing a lot of vector work in Unit 2. And then it sort of goes away a little bit in the Units 3 and 4, but as far as your physics studies go for Physics 20, Unit A and Unit B are the most important, and we're going to be spending the most time on them. Okay, Unit C is very important as well, and Unit D, I would put a smaller priority on Unit D. Okay, so force is a vector quantity, and this means you're fully described if you have two things. They are, of course, fully described by magnitude and direction. I was noticing on the test a lot of people just put like northwest or something, or south of west. You didn't even put an angle. Okay, so you have to do your direction fully and your magnitude fully for the full vector. Okay, so if we go back to our diagrams, Let's go back to this physics book here. Okay, let's label this diagram. Go back in your notes. Let's label this what they call a free body diagram. The upward force they call Fn, and we're gonna make a list of all the forces in a little bit here, but just bear with me. So that upward force is called the normal force. You notice that it's perpendicular to the surface. All normal forces will have this property. So if I lean on this wall, what happened? Was my velocity changing for a bit there?
Yes.
Then what happened? I stopped. So the forces must be balanced. Okay, so some variation of a gravitational vector, because I'm sort of on a lean, is hitting this wall. What's happening to the wall? The wall is pushing back, stopping my motion. So which direction does the wall push? Perpendicular to its surface. It's me standing on this floor. Why don't I fall through it to the center of the earth? The floor pushes back perpendicular to the surface. Okay, it's opposing this downward gravitational force, which we call Fg. Okay, so you can see that Fg is pointing downward, Fn is pointing upward, and we can just give it some random values. So 20 newtons down, and this Fn would be like 20 newtons up. So those guys are balanced. They're both 20 newtons. And then this force of friction, we can say maybe it's like 5 newtons left. And the unbalanced force will act to accelerate this object and change its state of motion. Okay, so let's just put that down. Unbalanced. That's acts. Okay, it's on there, not on my screen, but it's on yours. Acts on the book to change its state of motion. Okay, good. I think, are you guys sick and tired of the notes? Okay, I can feel it. Okay, we will do types of forces tomorrow. Okay, so let's enter the workbook, because I feel like you guys are had enough. Not until 3:26, buddy. Okay, so let's go into your workbooks, and let me show you what you need to accomplish. Okay, so Newton dynamics, it starts off on page, what is this, 67? Page 67 in your workbook. Okay, they're going to give you a little bit of notes, a little summarizing notes, pardon me. You know, it talks about Newton's first law. That's as far as we got today. Okay, then it's going to talk about Newton's second law, which we're going to talk about that more in depth. We're going to talk about the third law more in depth. We're going to talk about Fg more in depth. Okay, so what you're going to do is do some basic physics 10, basically from science 10. You're going to work with F equals ma. You're just going to get a feel for this stuff. So questions 1, 2, 3, 4, 5, 6, and 7, and 8, and 9, and stop. Okay, so you're going to stop at 9. You can cross out 10. In fact, any question that has the CD-ROM, I'm not going to make you guys do. So for homework, all you have to do is work on questions 1 through 9. Okay. And sorry, I'll just bring that up one last second. I'll just show you an example for question 8. Question 8, you have to use kinematics solve for accelerations, and then use your F equals ma. Okay? Only go to question 9. Okay? You guys comfortable with that? If you look at the first few questions, 1, 2, 3, it's probably just manipulating F equals ma. So nothing really challenging there. Let me just, before I let you go and before I ask your question, just quickly, guys, if F equals, come on, if F equals ma, how to solve for m? F over a, good. And how to solve for a? Just divide by m. That's it, okay? So homework is going to be super easy today. It's going to be a nice review of kinematics, and then apply it to this F equals ma. And we'll talk about F equals ma in more depth shortly as the week progresses. No. Okay, good luck.